Favorite sequences, actually. You know, last time we talked about the Fibonacci sequence, which is an important example of a sequence which doesn't have an obvious formula, at least not one which is convenient to use. As I said at the end, it does have a very weird formula that's not obvious at all, which involves things like the square root of 5. But here is another sequence. I don't know if you've ever seen this one before. This sequence is what I wrote before. When you're looking at the terms of this sequence, it is not actually very helpful to think of them as ordinary numbers, but think of them as sort of digit by digit. So when I see this, I see 1. This I think of as 1, 1 rather than 11. I mean, it is 11, but it's better in terms of this sequence to think of it as 1, 1. This is 2, 1. This is 1, 2, 1, 1. The next term is 1, 1, 1, 2, 2, 1. Now I don't have these terms memorized actually because I know the pattern. The pattern is very simple and it's something you can easily do in your head. So this is not some sort of very fancy formula for this. And I'm just doing the pattern in my head as I go. The next one is 3, 1, 2, 2, 1, 1. Anybody have any feelings about this? Anybody seen this sequence before? It's a strange.
Is this the one that correlates to the conch shell? Or am I completely off base?
No. It's that you may be thinking of the Fibonacci sequence. It does have something to do with sorry, I need to pin my my guy here. Oh. Thought I did. Oh, I did. Whoa, sorry. I'm making it worse. Okay, this one. All right. And then that. All right. Yeah, no, there is something about like the spiral. There's like there's a spiral based on the golden ratio, which can be expressed in terms of Fibonacci sequence because the Fibonacci sequence is related to the golden ratio. But actually, that's not this one here. Anybody else seen this one before? This is very strange, and you're unlikely to, in my opinion, I would have never figured out the pattern of this sequence if someone had not brought it to my attention. Here's a little hint. The name of this sequence, it has a name. This is called the Look and Assay sequence. The Look and Say sequence. The way you get the next number, it depends on the previous number. And the way you get it is by looking and saying. Anybody see the pattern now? I see someone. John Kroger.
I think I got it actually. Is it 1, 3, 1, 1, 2, 2, 2, 1?
Yeah, that's right.
Because you have 1, 3, you have 1, 2, and then 2 2s, and then 1, 1.
Yeah. I'm trying to, I don't know why it's popping up over here. Oh, maybe I do this. There we go. Yeah, what he said is exactly right. For the folks in the room which probably didn't hear him, the way you get it is you look at the previous sequence. For instance, this one right here, it says 2, 1. What you do is you look at the numbers that you see and you sort of count them up. What I see here is 1, 2, followed by 1, 1. And that's why this one says 1, 2, 1, 1. Right? You feel me? It's a little cute. What about the next one? So what I see here is 1, 1, 1, 2, 2 1s. And that's why this says 1, 1, 1, 2, 2, 1. Right? The next one is 3, 1, 2, 2, 1, 1, which is what you see here. So see if you can you try and write the next one down? See if you can write maybe 2 more. And I see my my person is here to take her test, so I'm gonna stick her in a room. Good morning, Gwen. I will be right back. Oh, he's back. Oh, it's because I left. Hey, Gwen. I'm going to chat you the test.
Okay.
You all ready?
Yeah, I feel confident about this one.
Great. All right. Can you see it?
Yeah, let me pull it up. All right, I got it up. Thank you.
Okay, yep. Now I gotta do this again. Sorry. Okay, I'm back. I'm ready now. Sorry about the interruption. So the next term should say 1 1 1 3 2 1 3 2 1 1. I hope that's what you got. You look at the numbers. Look and say. So the next one should be 3 1 1 3 1 2 1 1 1 3 1 2 2 1, something like that, right? It's cute, isn't it? What's interesting to me about this sequence is this sequence has actually been studied in depth mathematically. This was sort of invented and first studied by a famous 20th century mathematician, John Conway, who was at Princeton, did a lot of very fancy mathematics, but also did a lot of kind of cute and fun mathematics. He invented something called the game of life, which is not that board game, but another sort of a computer sort of simulation of life that maybe you've heard of. Conway, interestingly enough, recently died. He died of the coronavirus. It's like fairly early on, I think in April or May of last year. It's a shame. But anyway, here's some interesting facts that Conway discovered. If you look this up on Wikipedia, you will find a ridiculous amount of information. A lot of stuff is known about this sequence, and it has very interesting mathematical properties. First of all, Conway demonstrated that the terms are increasing. That is, you know, if you actually look at these things as big numbers, the number gets bigger every time. This seems like, from a certain gut reaction, it seems like they're kind of obviously going to be increasing. But actually, if you do the look and say, starting from some other points, they might not increase. For example, if I see well, here's one. If you start with 2, 2, then the next term would have been 2, 2, and then 2, 2 forever, right? So if you start at 2, 2, they actually are not increasing. Or if you start at 1, 1, 1, then the next one will be 3, 1, which is, as a numbers, is less than 1, 1, 1, right? But it turns out, and Conway demonstrated, if you start at 1, then it will actually increase, the numbers will increase every time. Here's another interesting fact. There are never, if you keep on doing this, never any 4s or higher. It's true in these examples that I did, but although I would encourage you to think about this if you're interested. Is it possible to ever get a 4 in there, starting from here? Of course, if you started at 1, 1, 1, 1, then you would get 4, 1. But we didn't start there. We started here. Conway demonstrated that if you start here, you're never going to see a 4 or any other digit. Actually, it will always be 1s, 2s, and 3s, nothing else. Interesting fact. Here's another fact that is kind of crazy to me. If you look at the limit, of course, since the terms are increasing, the limit of the sequence overall is infinity. That there is no limit. They just keep on getting bigger forever. But you can look at this limit. You divide each number by the previous number. This actually does have a limit, and it's a specific number that Conway computed. Like, you can compute this using a computer or something. He called this lambda, and the digits are something like 1.303 something, something, something. This is a computation that Conway did. And this number here is sort of is kind of like a new number. I mean, it's not like you can't express this number as in terms of pi or e or something like that. It has nothing to do with any of that. It's just some other number. It turns out this number is not a multiple, like I said, it's not a multiple of pi or e or a square root of 2, etc. It's not really related to anything. But Conway was able to demonstrate that it is a root of a polynomial, and so that there's a name for that. That's called an algebraic number. That's like, you know, like the square root of 2 is irrational, but it is algebraic because it's a root of a polynomial, x squared plus 2 equals 0, or x squared minus 2 equals 0. The square root of 2 is one of the roots of that polynomial. Or, you know, the cube root of 2. This is called degree 2 because it is a root of a polynomial of degree 2. This number is called degree 3 algebraic. I wrote an extra e on that because it's the root of a polynomial of degree 3, x cubed minus 2 equals 0. Conway demonstrated that this number lambda, this sort of new number that he found, lambda is a algebraic number. That is, it's a root of a polynomial of degree, I wrote it again with 3 e's, of degree 71. So actually, if you look at the Wikipedia article, you will see Conway showed that, and he actually wrote down there's a polynomial of degree 71, which has one of its roots is this number lambda. Very, very strange in my opinion. I myself, you know, I'm a mathematician. I prove theorems from time to time. I ain't never proved a theorem about a polynomial of degree 71. That's just very weird to ever even consider something like that. But it turns out this sort of ridiculous look and say sequence at some level has a lot to do with a polynomial of degree 71. Very, very strange. But that's a cute example of a sequence, in my opinion. Anybody got anything to say about that? As far as I know, not useful for anything in the real world, but fun to talk about. All right.
Professor, I know we've talked. Oops, sorry.
Yeah, go ahead,
I know
Bud.
we've talked a lot about sequences. How do these relate to series?
Yeah, so series, we're going to talk in depth about series eventually, but the distinction in the terminology, a series is when we sum a sequence. So when you add up all the terms of a sequence, that's called a series. You know, you've seen series. Well, I don't know if you've seen series before, but we are going to talk a lot about series. Just like sequences can converge or diverge, series can converge or diverge, and so on. But we're talking about sequences first of all. All right. What I want to talk about today in detail is a sequence can have a limit. All right, this I just mentioned right here. I was talking about here. This is the limit of a sequence, right? Now, you know that functions can have limits, but we haven't really talked yet about sequences having limits. But of course, it's not a shock to. I mean, I'm sure you thought that I was going to talk about this eventually. Anyway, for example, here's the sequence. Right, the sequence here, a formula for this would be an is 1 over n, right? Starting with n equals 1. And this sequence has a limit. Here, the limit, and we write it, you know, just like if you're writing limits of a function, right? Limit as x goes to, or limit as n goes to infinity of 1 over n is my sequence. What's the limit?
Would it be infinity?
I don't think so.
Or 0?
0, yeah. I'm tempted to say close. Infinity is close. It's actually 0. They're not very close, but yeah, it's 0, right? You can tell by these numbers here. They are getting closer and closer to 0 as you go down the list, all right? You can kind of see this graphically if you know, this is not a function, so we don't plot it the same way that we plot a function, but it's a sequence. We can plot the individual points as we go down the list of n values. The individual points are something like, the first one is 1, which I'll put up here. The next one is a half, so here's 1, right? Next one is a third, then a fourth, then a fifth, then 1/6, etc., right? So this is a plot of the points of the sequence. It doesn't make a line or a curve or anything because it's not like a continuous function. It's just individual numbers, one after another. But anyway, I think you can see, if you look out this picture as you go to the right, these numbers, they grow closer and closer to 0 as you go, all right? So let me just say, or here's another example. How about I want to talk about this sequence. 1, 1/2, 2/3, 3/4, 4/5, etc. So in this case, the numerator is always just 1 less than the denominator. Limit as n goes to infinity. If I were to write a formula for that, it would be n minus 1 over n, right? Or actually, if I do that, then the first term will be 0. I'll stick a 0 at the beginning, right? N minus 1 over n. And what's the limit of that? Well, these numbers, as you go down the list, they get closer to, what do you say?
Would it be 1?
Yeah, they get closer and closer to 1. So here, I'm going to say the limit of this is 1, right? Because these numbers get closer and closer to 1. Now, we should talk at least briefly about exactly what do I mean when I say the limit. So when I say lim n goes to infinity of some sequence a n equals some number L, L is like the answer that you get from the limit. Can we just say very specifically what this means? What it means is when the n grows very large, as n grows very large, this number an, the sequence term, the an grows, or it might not grow actually, because like the limit might be 0. I'm just going to say an will get very close to L. This is what we mean when we say the limit as n goes to infinity of an equals L. It means when the n gets really big, the an gets really close to L. All right? Now, I want to say something briefly about, like this, I hope that any of you would have said the same thing about what exactly does it mean. I would like to point something out, though, and this is something that if you become a math major, you will discuss this in much more detail in your later classes. But this business here grows very large and will get very close. Those two phrases there are being used in kind of an informal way. These are things that will, when I say as n grows very large, an will get very close. When I say those things, I hope that you know what I mean, but this is not real mathematical terminology. When I say these phrases, for example, when I say an will get very close, I would say from a purely mathematical point of view, I would ask you something like, how close, right? Like, what do you mean very close? I mean, that's not a mathematical term, right? Very close. If I wanted to be very specific about it, I would say, what do you mean very? Like, how close do you mean by very close? Do you mean like within a half? Well, no, that's not really close enough. Within 0.1? Not really. The answer to this question, how close, is kind of like as close as you want, right? Like, no matter how close you would want it to get to the limit, it does get that close. So however close you can imagine is getting that close. That's kind of what is meant when I say it will get very close. Actually, what I wrote up here is not really the true definition. I'm going to say this is sort of the informal description of what the limit means, but it's not a real definition. This is language that's used, say, in high school, or even, I don't know, people talk about limits before high school. This is language that's used. You tell a room full of kids this language, and they feel like they know what you meant, and you move on. And everybody more or less gets it. But I'm here to tell you, this is not really describing the mathematical situation very accurately. I think of this kind of description, talking about limits in terms of really big or really close, is kind of like when your kid asks you, where do babies come from? And you say something like, well, when a mommy and a daddy love each other very much, that's when the babies come from. This is meant to give the kids some kind of impression, but it's not actually the real story, right? Because you don't, for whatever reason, you don't feel like talking to the kid about the real story. This is similar language. We talk this way about limits because the true description of limits are a little more complicated. And we're not gonna get into this in much detail. Like I said, you are gonna take eventually other classes that cover this in much more detail. But I thought we should mention at least once the true definition. I'm here to tell you what the true definition is. I don't mind saying it. We're all adults here, right? We can talk about the mommies and the daddies if we really want to. The true definition of a limit is this. So what the definition has to include language about this kind of as close as you want idea. So here it is. This is going to look kind of crazy if you've never seen this before. It says for any number, when we write this definition, we always use this Greek number epsilon. That's what that little squiggly thing is. For any number epsilon greater than 0. This you should think of, although it's not part of the definition, you should imagine that this number is really small. And this number represents how close do you want the limit to get to the value L, all right? For any number epsilon greater than 0, which represents this sort of really close quantity or really close distance, there is some number n such that whenever the little n is greater than the big N, whenever is what that says, whenever the little n is greater than the big N, we have an minus L less than epsilon. All right, and you think of this n here, the big N here, as being really big. The beauty of this definition is that the definition doesn't actually say that epsilon is really small and that n is really big, because if you think about this, it's not necessary to say that. You're just saying for any number, there is some other number. So how you read this is that this part here, sorry, I broke across the line, but this part here, whenever n is greater than n, the meaning of that, the sort of mommies and the daddies version of this, is when the little n is really big. And then the meaning of this part, this says absolute value an minus L is less than epsilon. The thing, absolute value an minus L, that means like the distance between an and L, right? And we're saying it's less than epsilon, which is that really small number. So this part over here says an is really close to L, all right? So this is the true, like, formal mathematical way of saying that business, which is kind of nonsense if you look too closely at it. That business about when the n is really big, the an is really close to L. All right, this is the true definition of a limit of a sequence. There's a similar definition of the limit of a function, which maybe you saw in your Calc 1 class. I don't know. We're not going to use this definition. I will just say more on this in a course called Real Analysis. Real analysis is the mathematical field which has to do with real numbers and, in particular, concepts involving limits of real numbers is a huge topic in real analysis. And this is typically, you know, math majors take this in their junior or senior year. So a little something to look forward to. We're not going to try and get into the true definition. For our purposes, we're just going to think about, it's enough to just think of it informally. Anybody got any questions about that? Interesting fact, as you all know, the major concepts of calculus are based on limits, right? The derivative is a certain type of limit. The definition of a continuous function has to do with limits. The integral is another type of limit. These concepts were all invented by Newton, Isaac Newton, and also by a German guy named Leibniz. But the true definition of a limit was not fully discovered until the late 1800s. Newton was in like the late 1600s. So they did all of this without really understanding. They had the sort of mommy and the daddy love each other very much, that kind of understanding. Newton never really understood the true definition of a limit. But he was still able to invent calculus. Strange but true. The history of math is kind of twisty-turny like that. Anyway, I think that's enough we need to say about the true definition of limits. Anybody got any questions about that? I just wanted to bring this to your attention. We're not really going to get into it. As you can see, it's pretty complicated. All right, can I just say, when some language here, when the lim as n goes to infinity, an exists, we say an, the sequence converges, right? When the limit does not exist, which could be because it goes to infinity, or it could be just because it doesn't approach any particular number. I'll just say otherwise, we say an diverges. That means it doesn't approach a limit. Maybe it goes out to infinity, or minus infinity, or maybe it, for some other reason, it just doesn't have a specific limit. All right? One thing that you'll notice immediately, you know, I said lim, for example, like that first example that I said, lim as n goes to infinity of 1 over n is 0, right? This looks a lot like, so this is very similar to saying this, lim as x goes to infinity 1 over x. That is the limit, or this also equals 0, right? This is thinking of it as the limit of this is the limit of a sequence. Whereas this, I'm thinking of, this is the limit of a function. All right? These are very similar. They have the same formula, and you get the same answer. And they really are, this is not a coincidence, of course. When you're taking the limit of sequences, you can think of them in the same kind of way as you think of limits of functions. And you can even use same kinds of tricks to find these limits. You can use L'Hopital's rule even if you want to. So I want to just say sort of specifically about this. If our sequence an is a sequence with a formula that looks like a continuous function. You know, not all sequences have nice formulas, but some of them do. If an is a sequence with a formula that looks like a continuous function, like this one, for example, 1 over n, that looks like the function 1 over x, which is continuous apart from 0, but since we're talking about as n goes to infinity, we don't care about the fact that this is not continuous at 0. If an is a sequence with a formula that looks like a continuous function, then we can find the limit as n goes to infinity of an by doing the limit instead as x goes to infinity of f of x, right? If an happens to have a formula that looks like a function, then the limit of the sequence will be the same as the limit of the function, provided that these actually exist, right? If the limit of the function exists, then that limit will be the same as the limit of the sequence. All right, for example, if I want to do lim as n goes to infinity of 32 plus 3 over n, well, that sequence, it looks like a function, and so I can just turn this into the limit of a function. I can say this must be the same as the limit as x goes to infinity, 32 plus 3 over x, where now I'm thinking of that as a real valued function, not just individual numbers in a sequence, but as a curve, right? And then what is that limit? When we send x to infinity, that fraction has an infinite denominator, so it becomes 0. So this is just going to be 32, right? 32 plus 0 if you like, but it's 32. All right? And, you know, when you're writing this on your homework or something, we typically are not going to even bother writing this step in the middle, right? This is, I just wrote that now to indicate how I'm thinking about this, but you don't really need to say that part out loud, right? Or here's a more interesting one. Limit as n goes to infinity, n over e to the power n. Now this is a sequence, which is very strange to consider. E to the n, you know, the first term will be e to the 1, which is the number e, then e squared, then e cubed. Those are just, every one of them is a weird irrational number. But if we think of this as a function, as a real valued function on real inputs, actually this one is appropriate to use L'Hopital's rule. Because as x becomes infinite, we have a fraction here where the top and the bottom are both becoming infinite. And so if you want to find this limit, you would do L'Hopital's rule. So here I'm doing L'Hopital's rule. It turns into lim x goes to infinity of 1 over e to the x, and then this is 0, because now we have the denominator becoming infinite, while the numerator is just 1. All right. Right? I will just caution you, this doesn't always work. So you might get the impression that limits of sequences are always just easy. You just do them as if they were functions. But you can't always do that. For example, if I want to know the lim as, say, n goes to infinity of minus 1 to the n over n, all right? This one actually does not correspond to a real continuous function. So this can't make it into a continuous function. I mean, you would feel like this, right? It seems like that ought to work, but there's a problem with that. Negative 1 to the power x is not a continuous function of real numbers. I don't know if you've ever thought about this, but this is bogus as a real function, as a real valued function. It's not, well, it's just not a real valued function. For example, if you let x be anything in there, say x equals 1/2, this gives you the answer of minus 1 to the 1/2, which, whatever that is, it would represent the square root of minus 1, which is not a real number, right? Now, you can say that's the imaginary number, and it is, but in any case, this does not count as a continuous function of real numbers. And so, it doesn't make sense to think of this limit in terms of a limit of a real valued function. All right, so let me just say, this needs In order to find that limit, actually it does have a limit. The limit does exist, but this needs other techniques. I'm just trying to demonstrate. You cannot always translate a sequence into a function and think of the limit in that way. There are some sequences which have no function equivalent, all right? And certainly, you know, things like the Fibonacci sequence or that, certainly like the look and say sequence does not easily translate into a function, a continuous function. All right? Okay, great. So towards the end of talking about, sorry, one other thing I want to say. Sometimes when a sequence diverges, some divergent sequences I'll say in quotes first of all, go to infinity, right? So when it diverges, that just means it doesn't approach any particular number. Sometimes that's because the sequence is going to infinity or going to minus infinity. So in that case we say, or we write it this way, lim n goes to infinity of an equals infinity, all right? When the sequence values go out to infinity, that is to say, it means that the terms of an get really, really big, right? That's the informal way, at least, of saying what it means that the limit as n goes to infinity of an equals infinity. It means when you use large values of n, the sequence values also get really, really big. The true definition, which I will just write down and say not much about, it says for any big M greater than 0, there is some big N greater than 0 such that whenever n is bigger than the big N, we have an is bigger than the big M. So this, if you're interested, you can compare this to the true definition of the limit that I wrote earlier. You see no epsilon here. Epsilon in the other one represented a very small quantity because the terms of the sequence were getting really, really close to something. But this, I'm not trying to say the terms get close to anything. I'm trying to say the terms go to infinity, which means actually they don't get close to anything. Instead, they get bigger than any number. That's why this says for any number m, you think of m as a very big number. Eventually, we get an is bigger than that m. So really what we're saying here is that no matter how big you can imagine any number, eventually the sequence is bigger than that number. All right. This is the true definition of what it means for an to go to infinity. All right. All right. We got about 10 minutes. I think that's enough time to talk about, we have rules for limits that are similar to rules that you talked about for limits of functions. Rules for sequence limits. And these rules will help to find the value of a limit when you can't turn the thing into a function and find it that way. Rules for limits of sequences. These are the same rules, really, as function limits that I'm sure you talked about these in your calculus class. I mean, in your Calc 1 class. Anyway, here's what it says. If an and bn are both convergent sequences, so if an and bn both converge, then you can, here's the first one, you can add them together. So it says the lim of an plus bn is equal to the lim of an plus the lim of bn. So if an and bn both converge, then you can add them up, and the limit of the sequence when you add them together is just equal to the two limits of the individual sequences. before you added them together. All right, this is the rule about adding together two limits. Okay, and there's a bunch of other rules just like that. We can also subtract. So I'm going to write the same thing, but with subtraction. Lim n goes to infinity an minus bn is lim n goes to infinity an minus lim n goes to infinity bn, right? That's the subtraction. We can also multiply two sequences together. You might worry that we're going to have to do some kind of product rule. You don't. When you multiply an times bn, what you get is the lim of an times the lim of bn, right? You can also divide. Now the division does have a little caveat, but it's not a big deal. So the lim of an divided by bn is the lim of the an divided by the lim of the bn. And this works whenever the lim of the bn is not 0, right? Of course, if the limit of the bottom is 0, then this answer is not going to make sense because it would put a 0 in the denominator here, which is not allowed, right? I got two more of this variety. One is you can multiply by a constant. So this is also a rule that's true of function limits. If I have a limit of a constant times a sequence, you can factor that constant out of the limit. So this is the same as c lim n goes to infinity of an. This is for any constant c. All right? You can factor a constant out of a limit. And also, one last thing. Sorry, this is a big, boring list. We are only really going to say this once. You can do a similar thing with exponents. So the way to write this out is like this. The limit of an to the power p is the same as limit of the an on the inside, and then you raise the whole thing to the power, right? And this is true, you have to say some caveats here. This is true if p is positive and an is positive. If you allow the, if the an's are negative, then this gets messed up because you can get a situation like, you know, -1 to the 1/2, for example. If the n's are allowed to be negative, or if the an's themselves might have a negative limit, then the answer that you get over here might not be a real number. So that's why this says the an's are required to all be positive, because otherwise some weird stuff can happen, which we don't want to get into. All right. So this is the list of rules for limits. You should have them written down somewhere. I would say you should memorize these, I guess, although they're all, these are all things that you automatically do when you're finding limits. So you don't, we typically would use these without even thinking about any of them. For example, when I did, nobody even noticed when I used this already once today. I said this, right? And I said the second part becomes 0, and so all you get is just the first part. But really what I was doing at some level was I split up the limit first, plus this one. And then I said this one is 32, and this one is 0, right? So in my head, I was saying, you know, when you look at a limit of two things added together, you can just look at the limit of each part separately. And that was using one of these rules in the list. So this is why I say you should know the rules, but you don't really have to sit down and memorize them because you're going to just do them naturally anyway. All right? let's try a couple more fancier. So that's one example where we use the rules. Here's some more fancier applications of these rules. A good general trick for computing limits. For limits of fractions is put the n into denominators whenever you can. This is actually not just for limits of fractions. Can I just say for limits in general? Put the n into denominators whenever you can, because then when the n's are in denominators, then when you take the limit, something or other will become 0, right? Just like it happened in this example I just did. It's more convenient if the n's are in denominators, because then things will become 0 rather than things becoming infinity or whatever. So here's an example. How about n over n plus 1? All right. What can I do for the purposes of putting things in denominators? This is probably a trick that you've seen before. I'm going to divide through the entire fraction on top and bottom, divide everything by n. Another way of saying that is I'm going to start with this, and then I'm going to do like times 1 over n on top and times 1 over n on the bottom, right? The effect of this is to move every n into like a little denominator where it is. And so what do I get here? Lim n goes to infinity. On the top, I get n times 1 over n, which is 1. On the bottom, you got to distribute n plus 1 times 1 over n. It ends up canceling the n first of all and giving me a 1 over n on the second one, right? I distribute this here and here. And now we can do the limit, right? The thing, those ones are just going to stay like ones, and then the thing with the n in the denominator will become 0. Now, ordinarily, I would just say, I would expect you to just say it like that, right? You can take the limit everywhere. The ones stay like they are. The 1 over n part becomes a 0. This is how I would expect you to write it, but I just want to point out, when you did that step, you are actually using several of those limit rules. If I wanted to write out in complete detail, I would say, first of all, this limit of the fraction equals the limit on top divided by the limit on the bottom. That was the rule about limit of a quotient, right? And then this equals, well, that's just 1 on top, but downstairs, I split the limit up again, the limit of a sum. And then this is 1 over 1 plus 0, which is 1, right? Now, I wouldn't expect you to write out those steps, but I just want to, remind us that you are using that big list of formulas. It's just, they're so natural that you don't even really think about it, all right? I had one more, but maybe we'll stop with that, and we'll pick it up here next time. Some more examples of limits. All right, thank you for your attention. I hope you all have a good weekend. See you next time.
Thank you.
Thank you.